Hello everyone, I hope you're doing well. In this video, we are going to solve problem 6.3 or problem 3 from chapter 6 of Fundamentals of Statistical and Thermal Physics by Reif. So let's quickly get into the problem statement and we'll start the solution. Here's the problem statement. You can see on the screen. In first paragraph, they have told us what kind of system we have. So let's see what it is. A solid at absolute temperature T. We have a solid at temperature T is placed in an external magnetic field of H equals 30,000 gauss. The solid contains weakly interacting paramagnetic atoms of spin half so that the energy of each atom is plus minus mu h. Okay, so what kind of system we have is that we have a solid which is at temperature T and it is placed in a magnetic field of 30,000 gauss. Okay, now this solid is made up of many atoms and each atom, for example, so the situation is that we have a solid, for example, like that, and it is made up of many atoms. Let each circle is representing an atom. Okay, and if we talk about one atom, not all, each atom means we are talking about one atom only. Now this atom could have two kind of energies. One is plus mu h and the other energy it could have is minus mu h. Okay, now this energies, what kind of energy this atom has depends upon the spin orientation of this atom relative to the applied magnetic field. Okay, if the spin of the atom aligns with the direction of the applied magnetic field, then the atom energy would be minus mu h. This is what we call as if the spin is parallel to the applied magnetic field, then the atom will have minus mu h energy. If the spin is anti-parallel to the applied magnetic field, to the direction of the applied magnetic field, then the energy of an atom would be plus mu h. Alright, so we are talking about one atom only inside a solid. We are not talking about all of the atoms. We don't need to do that. We are just considering one atom and it has two possible kinds of energy. One is plus mu h and another is minus mu h, and this is the applied magnetic field. If it is a parallel case, then energy is minus mu h. If it is anti-parallel case, then the energy is plus mu h. That information will be used in part A as well as in part B. That is why I am clarifying it at first place. So I hope you are understanding what kind of system we have now. We have this solid applied magnetic field which is 30,000 gauss. We'll put it later on, and these are two kinds of energy that the atom, which is our system, could have. Now let's see what is required in part A and then we'll see the part B statement. And yes, in part A they are saying if the magnetic moment mu is equal to the 1 Bohr magneton, that is mu equals, they have given us the value of mu. Now we know the value of H, which is 30,000 gauss in energy, and mu is also given, which is 0.927 multiplied 10 to the power minus 20 ergs per gauss. Ergs is a unit of energy, but we have standard unit joule. We'll convert it into joule later. But we are given with mu and h. Now what we have to do is to below what temperature must one cool the solid so that more than 75% of the atoms are polarized with their spins parallel to the external magnetic field. So we have to find out temperature. Okay, there is an unknown which is temperature. We need to calculate temperature in this problem, and what else is given is 75% of the atoms are polarized with their spins parallel to the external magnetic field, which means when the probability of occupying the parallel state is 75%. Okay, we'll convert it into probability. So we are given with the probability, we are given with mu h, and we need to calculate t. Okay, we'll do it really quick. And in part B there is only one difference. Let's solve the part A first and then we'll do it for the part B. First we'll write the data. As I told you that if the spins are parallel to the magnetic field, I'm writing P, which shows parallel energy. If the spins are parallel, the energy atom has is minus mu h. If the spins are anti-parallel, AP, then the energy an atom would have is mu h. Okay, these are the two kinds of energy an atom could have in such a system, and we are given with 30,000 gauss. In part A, then you'll write part A, because the next data I'm gonna write is only for the part A, while this data is general to part A as well as part B. So in part A, we are given with mu, which is equals to 0.927 multiplied by 10 to the power minus 20 ergs per gauss. And we have 1 erg equals to 10 to the power minus 7 joule. So here I'll put the value of erg here, 0.927 multiplied by 10 to the power minus 20 multiplied by, in place of ergs I will simply put the value of erg, which is 10 to the power minus 7 joule per gauss. So it's simply 0.927 multiplied by 10 to the power minus 27 joule per gauss. Okay, we'll use this value. This is the data, and we are given with the probability of parallel states to be occupied is 75%. And when we convert percent into number, because probability is a number, not in percentage, so what we do is we divide it by 100 to convert percentage into probability. Okay, so since it was in percent terms, so we'll convert it into probability terms. 75 divided by 100 will give us the equivalent probability, which is 0.75. So the probability of parallel states to be occupied is 0.75. that is given, as you can see. So that more than, it means we just have to calculate when it is equal to, and then we can say when it will be more than. Okay, so we are finding here the temperature at which the spin states are parallel to the external magnetic field, parallel states. Okay, so 75%, and this is, and we need to calculate temperature. Now let's do the solution to part A. For that purpose, we need to calculate the probability. We know that probability of occupying a state EI is given by PI equals e to the power negative that energy divided by KT divided by whole divided by Z, which is the partition function. Let us call it as equation number 1. Now let's put the values right here. Probability for parallel state would be equals to e to the power minus energy of parallel state divided by KBT, KB Boltzmann constant, okay, and divided by partition function. And since we have only two energy states, so okay, I'll calculate the partition function separately. Here Z equals e to the power minus EP by KT. One is parallel state and another is anti-parallel state. So let's put these energy values here. Parallel state energy was mu minus mu h by KT plus e to the power minus, in place of EAP we write only mu h, minus minus becomes plus, so it's mu h by KT plus e to the power minus mu h by KT. This is partition function. Now let's put it right into this, put into 2. So probability of second state is e to the power minus, in place of EP I write minus mu h divided by kt divided by e to the power this mu h by kt plus minus mu h by kt, and we get minus minus plus by kt mu h by kt plus e to the power minus mu h by kt. This is probability of parallel states. Now to simplify it, I'm just gonna do that. I'm taking this in the denominator, so 1 is left here and its power is positive. Here it will become negative in the denominator, and in next step I'll multiply that power, that a term inside, so it's e to the power minus mu h by kt, e to the power plus mu h by kt plus e to the power minus mu h by kt, e to the power minus mu h by kt. In next step, its negative power and its positive power, they will cancel out and we'll be left with 1 here, plus both of them are equivalent, like it's same terms, so the power will become double, minus 2 mu h by kt. The power becomes double because the bases are same, power be added, and it's minus mu h by kt minus mu h by kt, it becomes minus 2 mu h by kt. Probability is here, and we need to calculate t. Okay, we'll separate it. I'm taking this term here and pp will be taken here, so it's 1 plus e to the power minus 2 mu h by kt equals 1 over p. I'm taking 1 here, it's plus, and it will become minus 1 on the other side of the equation, 1 over p minus 1. Now t is in the exponent, so to extract any variable from the exponent, what we do is to apply natural log on both sides of the equation. So we'll apply natural log on this side, kt equals natural log of 1 over pp minus 1. Alright, now it is the property of natural logs or logarithms in general that if we have a number, natural log of some number, and it has some power in it, then the power comes in the beginning as the coefficient. Okay, so let's do that. The power will come in the beginning, and the power was minus 2 mu h by kt. Natural log of e will be left, that is equals to natural log of 1 over p minus 1. Okay, natural log of 1 is equals to 1. You can confirm it in calculator. So we need t here only, so t will be taken into this side of equation and we'll take it here, so it's minus 2 mu h by k into natural log of 1 over p minus 1 equals to t. So we can write it as t equals minus 2 mu h divided by k, which is Boltzmann constant, natural log of 1 over pp minus 1. Let's put the values. Let's call it as equation number 3, and it will be used, the similar equation will be used in part B as well. Okay, in part B only the value of mu is different, rest of everything is same, so we'll use the same formula in part B. We just need to insert the values. So we have value of mu, h, k and pp. So let's put the values into this equation, putting values into 3. Minus 2 mu was the value of mu was 0.927 multiplied 10 to the power minus 27. H was 30,000 divided by k is Boltzmann constant, which is 1.38 multiplied by 10 to the power minus 23. Natural log of 1 over 0.75. pp was 0.75 minus 1. Okay, let's do that and see what answer we are gonna get. The result I got is 3.66 Kelvin, because everything was in SI unit, so the answer would be in Kelvin, SI unit. And 3.66 Kelvin, this is the temperature below which, this is the temperature at which the probability of atoms to be in parallel states, parallel to magnetic field states, would be 75%, and below that temperature the probability will be even higher. Okay, so below this temperature you write the statement as it was written on the question statement. Below this temperature the solid has more than 75% of the atoms polarized with their spins parallel to the external magnetic field. Value of natural log of 1 over 0.75 minus 1 come out to be minus 1.0986. okay, just for confirmation, so that this negative sign and this negative sign cancels out. Okay, you can do the rest of the calculation yourself. So let's start with the part B. All right, now let's see the problem statement for part B and do it quickly. And you can see here in part B they are saying, suppose that one considered instead of solid which is free of paramagnetic atoms. Now they are saying let's consider another kind of solid now which has many protons in it. Now in case of proton, the Bohr magnetic moment is different. Okay, for electrons the magnetic moment is different, for protons it's different. So they have considered another solid which is made up of many protons, and they are saying that now consider this magnetic moment. Okay, and calculate temperature at which more than 75% of their spins are aligned parallel to the external magnetic field. So it's the same thing that we need to calculate, but mu will be different in that case. So we will not put this value of mu but this value of mu, and first we will convert it into joule, and then we'll put into expression number 3 that we have calculated in part B. The similar result, the similar main formula would be used. PP is same again, H is same, but mu will be different. So let's do the part B. In part B, mu is equals to 1.41 multiplied 10 to the power minus 23 ergs per gauss, and we know the value of erg is 1 erg is equals to 10 to the power minus 7 joule. So we'll put the value of erg here, which is 10 to the power minus 7 joule per gauss, so that it is converted into SI unit, and it's minus 30 joule per gauss. From 3, putting the values into 3, sorry. Putting the values into 3, now T equals minus 2 mu, which is 1.41 multiplied 10 to the power minus 30, H 30,000 divided by K 1.38 multiplied 10 to the power minus 23 natural log of 1 over 0.75 minus 1. Now let's do it using the calculator. First we'll calculate this and then we'll calculate the rest of the things, and let me do it and I'll tell you people what result I got. I got 5.5802 multiplied 10 to the power minus 3 Kelvin. This is the temperature below which for proton paraffins, okay, for such a solid which contains many protons, this is the temperature below which all of the atoms spin will align parallel to the external magnetic field. Okay, the answer of this natural log of 1 divided by 0.75 minus 1 comes out to be minus 1.0986. okay, this is the answer of 1. This is equals to this. Okay, so that the negative sign, this and this cancels out and we get a positive result, just like we did in part A. Alright, this is it for the 6.3 problem. We'll do the next problems, and till then, take care and like, share and subscribe. Goodbye.